Thank you. So I'm going to talk about the fast user space OVS with afxdp. So I'll spend a couple of slides introducing the afxdp and how OVS use afxdp as a new netdev type, and then some performance optimization we have done. So afxdp stands for address family. XDP stands for Express Data Path. So it's a new socket type that allows user space program to send and receive packet at very high speeds compared to the traditional AF packet, the raw socket Linux support. So on the right-hand side, you can see traditionally we receive a packet. Packet comes from the NIC card, goes to the skbuf, to the Linux kernel stack, and then to the AFINet socket. Then the packet will be seen by your legacy application. So with afxdp, first we have Express Data Path, the XDP program inserted into the NIC driver. And when NIC driver receives the packet, the XDP program will create a fast channel to forward this packet to your user space program, which create an afxdp socket interface. Then your application can receive a packet at user space. So user space program need to manage RX ring, the receive ring, and transmission ring of the afxdp packet, and also introduce something like fill ring and completion ring to interact with the afxdp packet. So with driver support, zero copy can be achieved, so which means that the packet can be directly DMA from your device to the user space program, so that the performance could be amazing. For example, they are reporting ingress, egress performance larger than 20 million packets per second. So in case of OVS, we want to use afxdp as a packet I/O, as a way to receive and send packet. So the idea is very simple. So we, at the OVS user space program, we create an afxdp socket. And then we'll have to attach an XDP program to the device driver. And then when packet comes into the NIC card, then OVS afxdp socket will receive the packet. Once we receive the packet, then we create the same interface as we use by the OVS DPDK today, the dpif-netdev. And then we do the rest of the flow processing, the parse, lookup, action in the user space. So this is the OVS architecture. So we have a netdev layer, which is an abstraction layer for the network device. We have dpif, stands for Data Path Interface, and we have dpif-netdev, which is the user space implementation of OVS, the Data Path implementation, and it's also the same code used by OVS DPDK. So in this work, what we introduce is we add a new netdev type called afxdp. And at Linux kernel part, we no longer use kernel module, but instead we insert an XDP program. And the program is very simple, just to forward the packet as fast as it can to the user space afxdp-netdev. So for configuration, it's very simple. So you do configure, make install, and then you add a bridge BR0. And the data path type is netdev. And then you can add a port. So this port, in our case, is EMP2S0. And then you say type is afxdp. I post my v3 patch at the mail link list, so based on the command line. So we start to do the performance prototype evaluation. So on the left-hand side, we have a sender. So sender is using metronome NFP 4000 to send 20 million packets per second to the server on the right-hand side. So on the right-hand side, we run OVS with afxdp user space data path and with Intel XL710 40 gig Ethernet drive. And we measure the performance result using single core and using single UDP flow. So since we are sending 20 million packets per second, so our first performance goal is to see whether we can get 20 million per second for receiving at the OVS. So, however, to get 20 million packets per second, it's actually pretty hard. So if you do the math, 20 million packets per second means for one packet, you only have 15 nanosecond budget to process the packet. And usually to process the packet, we have to do a lot of things like initialize this data structure, set up that field, initialize your base pointer, set up the packet length, for example. And in my test bed, I have a 2.4 gigahertz CPU. So, which means that for one packet, I only have 120 cycles budget for processing a packet. And if you do a lot of things, and then you'll see a lot of catch misses. Every time you try to access this memory or do whatever, it's a memory access. So catch misses takes somewhat about 32 nanoseconds. If you have a lock, just the lock prefix, not lock contention, then it takes about 8.8 nanoseconds. And if you do system call, then it's even worse. So it's taking about 75 or 42 nanoseconds, depends on your setup. So we can do batching, but batching, for example, today we do batching of 32 packets. So it makes the case a little bit better. So if we do batching of 32 packets, then per batch, our budget is about 1.5 microseconds. So we want to see that our implementation or this new afxdp netdev type can meet this time budget. So the first optimization we apply is called PMD. So in the OVS, so afxdp is a socket, so it returns you a file descriptor. So one way is to pull this file descriptor when there's a packet coming in. But calling a pull system call, actually it's a system call, so it has pretty high overhead. So instead we use a dedicated thread, the PMD thread, to do this. So luckily this is very easy to implement. Just set the flag to be true. So the second optimization is that for every packet I/O packet coming into OVS, we need metadata. In our case, it's a struct DP packet. So first is that we try to do memory allocation and metadata initialization as much as we can. So we do DP packet pre-allocation and pre-initialize all the DP packet fields. And also for the memory location of this DP packet, we want them to be all together in a continuous memory, so that every time we try to set up a batch of 32 DP packet, we don't incur extra cache misses. So hopefully first packet we suffer from the cache misses, but then the second one, the subsequent one can benefit from the miss overhead. And then we have following a couple of optimization. For example, we have to implement a memory pool for afxdp. And then we have to make sure it's the data structure we use is fast enough. And then there's a packet data buffer for the afxdp. So instead of using a shared buffer, we use dedicated packet data buffer for each queue, so that we can avoid the lock. Finally, for sending a packet to afxdp socket, we have to issue a system call. And issue system call is very, very expensive. So we have to batch it. We have to do very aggressively batching the send system call. So we have more detailed analysis in the recent report from the Linux Plumber below. So with this optimization, so we start to measure the performance. So first is very simple. we create a bridge, BR0, and then we attach a device, EMP2S0. We install a single flow, just say import equals to this EMP2S0, and action is dropped. So when packet comes in with 20 million packets per second, we obviously still do parse. So extract the flow key and look up the flow table, and then action equals drop. So we want to see how fast we can do. So we have a pretty cool command called PMD state show. So for this experiment, we can see first that subtable lookup per mega flow hit is always 1. So we are always using single flow, single DP packet, so it's always hitting EMC, so there's no extra mega flow hit, mega flow lookup. As a bottom line, we want, it's the most important, so average processing cycle per packet is 124. So this is good. So remember our budget is 122, sorry, not nanosecond, 120 cycles for the 20 million packets per second. So Rx drop, we are close to 20 million packets per second. So if we want to do a breakdown of this CPU processing, then we run perf. So perf shows that we spend 26% of CPU time on the Linux ISQ, the receive function, and about 26% of time on dpif-netdev input, and also 24% on mini-flow extract. And the blue one, human element push, is the overhead introduced by the memory pool I mentioned before. And for CPU utilization, it's 200%. So 100% is used by OVS DPDK, and 100% is used by the kernel's software IRQ daemon. So right now we are not, unlike DPDK, which offloads the kernel module. Right now we are still running the OVS. We are still running the device's driver. So this software IRQ daemon is still processing the packet, processing the incoming packet at the NICAS driver. So the next experiment is to do L2 forward. So it's simple. It's similar, but this time we do a different flow. So we say import equals to this EMP2 S0, but actions we say, okay, change the input port to another number, and then change its source MAC address, and then output to the same port as it received. So again, we run PMD state show, and this time, because we are doing sending, so sending, first we want to make sure the average packet per output batch. The maximum is 32. Right now we get 30.57, which is probably okay. And then the average cycles per packet we spend is about 180. So compared to only doing receive and drop, we are doing receive and send. So receive and drop takes about 124. So here we see 180. So probably another 50 cycles are spent for sending the packet out. Again, perf record shows that right now we have extra overhead. 16% of CPU is using at NetDev Linux send. And the others are doing the receive. So for the last one, we are doing PVP performance test. So in this setup, we first have a BR0 and with EMP2 S0 port attached. And then we run QEMU 3.0 with vhost user. And then right now, we don't have a vhost user implementation, so we have to compile our code with DPDK. So we are using DPDK's vhost user implementation. And then we start a VM with Ubuntu 18.04 using VirtIO device. And inside the VM, we are not running test PMD, but we are using a feature called xdp redirect. So xdp redirect will receive the packet at the driver side and then just do nothing and send the packet out to the VirtIO network device. So it will send the packet back to the VirtIO driver. So first, CPU utilization. This time we use 300%. So one extra 100% is QEMU system running, which runs the virtual machine. Then again, PMD stakes show this time we have average packet per batch is a little better, 31. There's no cycle idle, and this time we have cycles per packet increased to 360. So again, we want to understand where does the cycle span. So perf again shows that this time probably we spend extra 30% or more on the RTE vHost DQ. So vHost DQ is for OVS to receive packet, and vHost InQ is for OVS to put packet into the virtual machine's VirtIO ring buffer. And I also see that we have a DPDK do TX copy. So this is because in the case of pure DPDK environment, every packet has an mbuff. But in this case, because the packet is created by afxdp and it doesn't have an mbuff structure, so when forwarding the packet to the vHost implementation of DPDK, then it has to copy and create a new mbuff. And mini-flow hash 5 tuple is also showing up here because usually, like in the case of DPDK, there is a RSS hash provided by the underlying layer. But in the case of afxdp, there is no such metadata provided, so we have to recalculate the RSS hash. So this slide summarizes the performance number. So for the OVS afxdp, we can get 19 million packets per second for RX drop. For L2 forward, it's 14 million packets per second. For PVP, it's 3.3 million packets per second. Compared with DPDK, so this is based on the document below, not on my setup. So compared with the document, it's probably L2 forward is similar, but then PVP right now it's still slow. But I think it's because of the mbuff use case different. I also provided some demo video in the link below. So in conclusion, afxdp is a new socket type for Linux, in the case of Linux, to receive and send packet at very high speed. And in this work, we add support, a new NetDev type to use the afxdp. And we receive and send packets through this afxdp interface, and then we reuse all the existing user space data paths used by OVS DPDK. So imagine the new feature added to the user space data paths can also be used by this afxdp-netdev interface. And to get high packet rate, it's pretty hard, so we have to do a lot of performance optimization. So we have to do pre-allocation and pre-initialization as much as we can. And so we have to batch processing of all the packet. So pre-allocate and pre-initialize actually will reduce the number of operations we need to do per packet. But actually, batching does not. But batching plus a cache-aware data structure can amortize the cache misses, so that we only pay for the overhead of cache misses for the first packet, and then the subsequent packet can benefit from the cache line there. And for this work, sometimes a lot of cases that people cannot deploy DPDK because DPDK has a lot of requirement, for example, dedicated CPU or dedicated device. So I would like to say afxdp could be another alternative for people who want to get higher packet rate, but could not deploy DPDK. So the performance right now is still slower than DPDK, but there are more optimizations coming to the Linux kernel community, so we can improve it later. So compared with DPDK, I would say that this model use afxdp is more Linux kernel friendly. So it has better integration with the Linux kernel and management tool. So you still have your Linux driver, device driver there. When you run ifconfig or ip-link, you'll still see your device there. So all your management tool will be still available. And sometimes it also provides you a chance to reuse the kernel's feature. Because there is an XDP program inside the kernel, so you can say that for this program, I want to use afxdp fast channel to the user space. For another set of packets, I can still reside in the kernel and do the rest of the processing using the kernel stack. So it's unlike DPDK, which in the beginning you have to say whether I want all packet in the user space, and later on probably you have to re-inject the packet into the kernel to use some features, for example, the KNI module. And so right now, although we are using the PND, which spins the CPU, but it doesn't require dedicated CPU, or it doesn't require dedicated, it doesn't require a huge memory page. Okay, thank you.
All right, we have time for questions. Go ahead.
I'm confused. You implemented a new Userspace NetDev, right?
Yes.
It's not a dpif-netdev.
We are reusing the OVS, the datapath in Userspace. Yeah.
But I saw you build OS with dpdk.
Oh yes, yes. So that one is just for using the vhost implementation.
Okay.
Yes. Yes.
So actually, it doesn't depend on dpdk.
Yeah, it doesn't depend on dpdk. If you don't want to use vhost user, then you don't have to build with dpdk.
Okay. Got it. Actually, dpdk also implemented afxdp PMD driver.
Oh yes.
Maybe
yes.
you can try that.
Yes.
I think it's similar.
Yes. So there is another work that adds support, afxdp support to dpdk. So yeah, that's something also can be used.
Okay. Thank you.
Thank you.
So I was impressed that getting it to do PMDs for afxdp was just a matter of setting a flag. That I'm pretty sure that PMD support was added for dpdk, so it means that support must have been done right.
Yes. So right now,
William, impressive performance analysis work you showed. Thank you for that. And I wanted to explore a possibility that did you give a consideration to the scheduling algorithms and bringing in additional cores? So potentially you can have added latency, and then increase the per packet processing budget and increase the overall system throughput. Was any consideration given to that?
yes. So I don't have. So right now I don't have a solution. So your question is whether I can have some ways to balance the CPU cycle spent on the packet. So
yeah,
right now,
add more cores.
Okay.
Add more cores, and right now in the analysis you presented, we had 150 T-states or cycle per packet budget. So maybe if 2 packets are coming, and give it to 2 more cores and potentially increase that budget and then do more processing. I see, yes. So yes, there's something I should try later. So using more PMD threads to do parallel to see if the performance number scale, something like that. Yeah, awesome. Thank you.
Thank you.
So I interrupted when you had an extra comment earlier. Did you?
Oh, Yeah, so I want to say that right now, when you compile with dpdk, actually the packet metadata is either, we have a if defined there, so it's either dpdk's mbuf metadata defined or the other. So in this world, it's kind of mixed. So we receive a packet from non-dpdk case, and then we have to forward it to dpdk mbuf. So there are extra overhead there.
Let's thank our speaker one more time.